This is Project 21037, Apparatus to stimulate tumor environments and reproduce organs using an interactive and dynamic system, aka asteroids. My name is Connor Nimitz. I'm the systems engineer and team lead.
Eric Tollefson, biomedical engineer and team procurement lead.
Amida Alsef, and biomedical engineer.
Nick Bai, biomedical engineer.
Tyler Hertenstein, biomedical engineer.
Nick Watson, electrical and computer engineering.
This poster board demonstrates the team's effort and results throughout the year. It displays the results which were collected through the verification process. However, due to COVID-19, this video will address the information found on this poster, which is typically the centerpiece for Design Day. Our primary stakeholders are Dr. Jerome Lacombe, Dr. Frederick Zinhausen, and Alan Norstedt.
The ANBM is trying to culture tumor organ cells in a closed environment using an apparatus to stimulate tumor environment and reproduce organs using an interactive and dynamic system. Each apparatus consists of a middle T-block component of the chip which holds the organoid cells, as well as two manifolds which hold artificial cell membranes capable of receiving either fibroblast or endothelial growth media. To make the system more efficient, the team is implementing a design of the system which can hold 6 of these chips and are able to be seated at 37 degrees Celsius simultaneously. Further, we're optimizing the heating element and vertical stabilization of the 6 chips carrier. Here we have the original setup used by the ANBM. We can see 2 asteroid chips each connected to media through a pump and tubing system. To seed each chip, they first get sterile chips, put them in the chip carrier and prepare them with agarose and incubate for 15 minutes at 37 degrees Celsius. Then they vertically stabilize the chip carrier at plus 90 degrees along the y-axis and coat the first membrane with collagen, incubating for an hour. They rotate the chip carrier 180 degrees along the y-axis again and coat the second membrane with collagen, incubating for another hour. After that, they inject the chip's first membrane with endothelial cells while it is stabilized and incubate for an hour, and inject the second membrane with fibroblast cells and incubate for an hour. Finally, they place the chip in a horizontal position and seed the organoid cells into the middle T block. After connecting the chips to the pumping system and setting over a heating element, the chips are prepared.
We'll now take a look at our system overview. The optimized asteroid system is split into 3 parts: the heating element, which controls the temperature of the media, a vertical holder, which supports the chip carrier at 90 degrees, and the tubing system, which can easily be removed and attached. Moving on, we'll share our system block diagram. This shows the interfaces between the different components in our system. I'd like to emphasize that the tubing system is attached when the chip holder is on the heating element, and this is all separated from the vertical holder that we've created.
So these are the system requirements that helped us develop our system, highlighting the minimal viable products. The first one for the heating element, the second one for the fluid flow and the tubing connections, and the third one for the vertical stabilization holder. And here is the rest of the system requirements that we have. We applied the agile process that uses the concept of iteration and adaptation. We had bi-weekly Scrum reports, and tasks were planned in smart sheets that helped us reduce the risk and increase our flexibility and got us immediate feedback. We applied this to PDR, ISR1, and ISR through ISR3.
The first step in our design process was to develop an asteroids chip carrier that would carry up to 6 chips and allow for all 24 tubing connections to insert onto the chip. This design featured hinge walls, symmetrical chip spacing, with no real weight to prevent chips from falling all the way through if the carrier was lifted off the surface of the hot plate. It also featured an open top design, which led to massive loss of heat. This design met system requirements 4.1, 4.5, and 4.6. The second design for the asteroids platform featured a removable chip carrier, which would sit within a walled housing to still provide tubing access. This design included the addition of vertical stabilizers to ensure the chips are held in upright positions, a lid to improve the thermodynamic environment, and uses the same hinged walls from previous iterations' designs. This design met all previously stated requirements, as well as system requirement 4.2, the maintenance of 37 degrees Celsius within the chamber. The third iteration of the asteroids platform showcases the new asteroids chips manifolds, shown in orange on the figure to the right of your screen. These tapered manifolds would allow for the chip to slide into the newly designed chip carrier, providing a hard stop once the chip reaches and sits flush with the bottom of the chip carrier. This design ensures that the chips are secured in both their X and Y axis and maintain full contact with the surface of the hot plate underneath. This design met all previously stated requirements, as well as system requirement 4.7, the use of a microplate reader for image capturing. The final product that we developed and delivered to the research team at the Center for Applied Nanobioscience and Medicine in Phoenix, Arizona, was a combination of multiple design aspects focusing on improving the ergonomics of the product. This product utilizes the third design iteration of the chip carrier, which features the taper lock manifolds and removable rectangular walls, with 3D printed couplers which press firmly onto the chip's inlet/outlet ports, providing a leak-free seal. The walls are tapped and threaded with a Nordson Medical 1/4 inch hex to hose barb adapter, and this external hose bar provides a firm and leak-free attachment of tubing to the system. The entire platform's footprint is the same as that of a 96-well microplate, in order to allow for the platform to be placed within a microplate reader for imaging through the asteroid's chip's central channels. The final asteroid's carrier is able to be held upright 90 degrees by our 3D printed carrier, while resting for an hour during the cell seeding process. Finally, the design features hollow cutouts wherever possible to save material and speed up print times. The final design met all previously stated requirements, as well as the final two system requirements, 4.3 and 4.4, regarding vertical stabilization and minimum fluid flow rates with no leakage of media.
Moving on to the results of the overall experiment, we had to confirm the hot plate would reach a temperature of 37 degrees Celsius, and it did, and it also did not deviate with plus or minus half a degree. Here's a product video of the overall system working of system 2, and as you can see, there's fluid flow going through as the lid will get revealed of the chip having that direct connection. Next, talking more about our tapered system that would be able to be removed all at once. There's no leakage during this product, and there's also a tapered and tailored connection for this perfectly for the asteroid system. Going on to the full assembly, we can see that it is very easy to use and it's very user-friendly. All those connection points get removed at once, making it so that all 6 chips can be removed at the same time. For demonstration purposes, there's only 2 here. And finally, all requirements for our SRVM were verified successfully from these experiments.
Throughout the last year, we've learned many lessons. Some of these are utilizing the agile development method, dealing with long lead times that delay designs, learning the ability to bounce back after receiving poor feedback on our initial deliverable, and the ability to communicate in a virtual environment. Throughout the last year, we've had 4 major deliverables, beginning with our preliminary design review, leading into 2 ISRs where we presented our progress throughout the year, and ending with an FAR presentation where we showcase our completed design.
In this presentation, we discussed the introduction and stakeholders, the optimized asteroid system, agile methodology, the optimized asteroids design and delivered products, the deliverables over the past year, lessons learned. The team also has met all requirements that the customer has given us. I and Team 21037 would like to thank Sharon O'Neill, the Center for Applied Nanobioscience and Medicine, and Alan for all the help and support that we received throughout this project.